Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Hello and welcome to Lost in Science for another week. My name is Claire and I have to say it is a very special edition of Lost in Science because it is the first time that we are all back in the studio together. Chris?
For 2020.
That's right, for 2020.
I just did too many 20s there.
I think you added one too many 20s.
20s.
Yes.
I've really enjoyed this month so far because it's lots of twos in the dates.
It's a very auspicious month, isn't it?
Yeah. 20,
for a number of reasons.
Yeah,
one of them being that, we're all back in the studio this week.
Finally.
Yeah.
Finally.
Yeah.
Yeah. It is great. 2020 is off to a very slow, lagging start for Lost in Science. So thank you for being with us. This week on the show, I am speaking to Professor Jared Cole, who's a self-described pragmatic theoretical physicist, quantum physicist, and he's doing a whole lot of research with Exciton Science, so the Centre for Excellence in Exciton Science.
Pragmatic?
Yeah, pragmatic, practical.
As opposed to
some other theoretical physicists.
you don't want to point the finger at.
Pointing the finger at you, Chris.
It is an interesting idea, though, like a practical theoretical physicist.
It is, isn't it?
Yeah,
it is an interesting idea. Someone who can apply their theoretical knowledge to make new things. He's an inventor, and his research is all about inventing new ways to make more efficient solar cells using quantum physics.
So he'll tell us what an exciton is and how it works for a solar cell?
Yeah. Maybe,
Excellent.
For some more detailed... in-depth physics, I suggest maybe you get in touch with him independently, Chris.
That would be the pragmatic thing.
That would be the pragmatic thing to do.
Yes.
Yeah, for the first time in your life. Chris!
Hello, Claire.
What do you have for us today?
Well, I think we said last week that we're still catching up on stories from over the summer. There's been a lot of science over the summer, and I have a story that came out that broke, I think, in January this year, and it's about global cooling.
Don't troll us.
No, I'm not trolling you.
Us.
Global cooling of human body temperature.
Right.
Apparently, there are people saying that we are getting cooler.
So how are you going to believe a group of scientists saying they're getting cooler? Yeah. Okay.
Great point.
Yeah.
Hey, it's not the first story I've done on the science of cool, I'll have you know, Stu. No, this is, they had the data to prove it. They've got graphs, they've got regressions, they have...
lots of statistical analyses.
Cool.
and they can back it up, dating all the way back to the 19th century. So, we're doing the proper deep dive.
Certainly sounds cool.
Mm-hmm. So anyway, we'll be, it's a very fever pitch kind of story that we'll be taking the pulse of.
Well, it's good for us all to be back, and on with the show. So there is no doubt that solar energy will continue to play a huge part in renewable energy generation and help get human carbon emissions to zero. But how do we make sure our solar cells are converting energy efficiently? Well, my guest today has a couple of thoughts, I'm sure. Jared Cole is Professor of Physics at RMIT University and one of the chief investigators at the Australian Research Council Centre of Excellence in Exciton Science. He's also a self-described pragmatic theoretical quantum physicist. Jared, welcome to Lost in Science.
Thank you. Thanks for having me.
Great to have you here, especially I don't know many pragmatic theoretical quantum physicists, so maybe you're the first one to be on the show. let's start at the start. We're talking about solar cells. So the solar panels that you see on people's roofs that we're familiar with, how do they currently work? And how efficient are they?
So most solar cells work, at their heart, obviously, they need to convert the light from the sun into electricity. And the way they do this is most of them, particularly the ones on people's roofs, are made from silicon, or the majority of the cell is made of silicon. And silicon has this special property that when you shine light of the right colour on the material, it generates electrons, which can then be sucked off to allow to generate electricity. And so this principle has been known for a very long time, and the way modern solar cells work pretty much are the same as they have for 30, 40 years. And so the light into electricity conversion in the silicon is governed by how silicon is structured, what we say is what the electronic structure of silicon is, how the electrons move inside the silicon material. And at the moment, they're kind of about 20% or so of the light from the sun is converted into electricity. And this is related to how much of the sun's light they can actually absorb and how much is wasted by not being absorbed by the silicon.
I mean, given silicon's got its own structure, is there only so much that you can, mess around with that to increase the efficiency?
Yeah, so it turns out there's some very fundamental limits that are placed on how well silicon solar cells can work. And the upper limit is about 30 or 33%. And it's the laws of quantum mechanics tell you that you can't absorb too much energy because the solar cells just heat up and they don't convert that into electricity properly. And you can't absorb too little energy because it acts like a barrier. You can't get over the barrier to generate the electricity. And so this is kind of the modern solar cells are getting quite close to the theoretical maximum for silicon. And so this is one of the reasons why pretty much all the modern solar cells are about the same level of efficiency.
Right. I mean, so in some cases we're sort of in a really good place because we are getting close to that sort of, I guess, maximum efficiency. But in another sense, it's like, well, how are we going to break through that efficiency?
Exactly, yeah. So one of the ideas we have is if we can get away from silicon, because this fundamental limit of 30% is specific to silicon. And there are a few other materials that might work in better ways. So silicon is what's called a semiconductor, and there are a few other semiconductors, but they're usually pretty expensive or they're difficult to work with. And there's been a lot of research on making solar cells out of them, but it hasn't produced a lot of results as of yet. Certainly not industrial-grade solar cells. So what we're looking at in the Centre for Exciton Science is developing new molecules that you can add either on top or underneath one of these silicon solar cells, which convert parts of the light that aren't converted by the silicon. And so either you absorb some energy and then convert it down into energy that can be used by the silicon, or you absorb energy and convert it up, depending on which end of the solar signal you're looking at.
So this sounds to me like a pre-digestion or a post-digestion sort of situation.
That's a very good analogy, actually. Yeah, you want to kind of modify the sun's light so it's more accessible or more digestible by the silicon. And so at the moment, this is one of the leading ideas how we might be able to get a significant amount of the energy of the sun. There are a few other possibilities for how this might work, and some of them are in industrial products, but they still have their own limitations, or they're very expensive or complex, or they don't live for very long. Of course, you want a solar cell to continue working for 20 or 30 years, ideally, once you put it on the roof. And one of the big challenges is making long-lived solar cells.
How do these molecules that you're talking about work? Do you apply them like a paint and...
Well, that's actually one of the unsolved problems at the moment. The idea would be to have some kind of film, either during the manufacturing process, you want to have a layer of silicon and then apply some coating above or below, or you want to build a solar cell that's made up of layers, and each layer does a different part of the process. And so one of the One of the problems is getting these molecules tuned to do the right amount of modifying the sun's light. And another problem is making sure these molecules are stable and, as I say, don't degrade over time. And so there's some really difficult challenges there in terms of the chemistry and in terms of the material science and the engineering. And that's what we're working towards.
Now, I would be remiss to not ask you about what exactly you're part of the Exciton Science Centre for Excellence. What is the word Exciton? What does it mean?
So this is one of these words that is very well established in chemistry and physics, but it hasn't really made it out into the general public. So an electron is, of course, the particle that electricity is made from. And then in semiconductor physics, we also have the concept of a hole, which is the lack of an electron. So if you take an electron away, what's left is the hole. And it turns out when electricity flows, particularly through a device like a transistor or a computer chip, it's important where the electrons flow and where the holes flow, because they flow in the opposite direction. When you absorb energy into a molecule, you actually create both, or you promote an electron up to some excited state and you leave behind the hole. And these two together form an excited state, which we call an exciton. So it's just a shorthand scientific way for saying how do we manipulate the energy that's stored in molecules.
Thank you very much. Now, energy, greenhouse gas emissions are big on people's minds at the moment in Australia and around the world. But particularly in Australia, what should communities be looking forward to in the future when it comes to renewables?
Well, I mean, if we do our job right, as with all technological developments, sometimes it's a big step forward and people notice, like an iPhone. That was a huge step forward, even though it was made up of lots of little bits of technology that kind of already existed. But sometimes technology developments, people just don't notice. Just all of a sudden they discover that when they buy their next solar panels for their next house, or they add a few more solar panels to their house, they are cheaper and they produce more electricity. And that's what we would be looking for. We'd be looking to help develop new photovoltaic devices and also new lighting and all sorts of other more energy efficient devices, which would just slowly be rolled out into people's houses and workplaces, the same way that we swapped our incandescent light globes for LED light globes and almost no one noticed. Yeah, they have a slightly different colour and our electricity bills went down. But that was about all that happened. They just slowly replaced all the old ones. And it's relatively difficult to find an incandescent globe these days. So if we do our job right, the same thing will happen with the solar panels. There'll just be more and more of them, and more of our electricity will come from those photovoltaic cells instead of from coal and gas and other non-renewable sources.
And Jared, what is the thing that I guess most excites you about the Exciton Science field?
Well, I mean, you said at the start, I talked about being a pragmatic theoretical physicist. So a lot of people go into theoretical physics because it's a very esoteric subject, it's very fundamental. You learn about how the universe works. Physicists kind of pride themselves in, our whole profession is about developing mathematical models for how the universe works. But I kind of have a much more pragmatic approach to that, which is I like building things. I kind of am a frustrated inventor at heart. But I also like computers a lot, so I build computer models to help us design new devices. This is what I get very excited about, is thinking up new things, doing the calculations, doing the computer models to find out whether they work and how well they work, and then talking with experimental groups, other people in the centre and the other people at my university and my colleagues all around the world. We then develop new experiments and hopefully new devices that kind of put these ideas into practice.
Well, that is definitely something to be extremely excited about. Jared, you also have a public lecture series, or the Centre for Excellence in Exciton Science has a public lecture series coming up at the Victorian State Library. I love the name. It's called Light Conversations. Can you tell us a bit about it?
So this is an idea where we want to kind of get across the key principles and ideas behind what we're doing to the general public. Of course, we spend a lot of time talking about our science to other scientists, but it's also important that the general public and the people without a lot of training in sciences understand what it is we're doing and why we're doing it. This coming lecture is going to be myself and Professor Dane McCamey from the University of New South Wales, and we're specifically going to talk about this question of how quantum mechanics helps us convert sunlight into electricity, how it limits us, and how it might actually allow us to do even better. And it's this multi-stage process of, we already use quantum mechanics to understand solar cells. That understanding also tells us the limitations, but hopefully it will also give us a way to sidestep these limitations and ultimately give us better devices for harvesting solar energy.
And Jared, where can people get more information about the lecture series?
So this Thursday, the 27th of February, at 5:30 p.m, the lecture is at the State Library. You enter off La Trobe Street, down the side of the State Library, and there will be drinks and networking afterwards, and a Q&A session. And the lecture itself will go for about an hour, and then there'll be questions afterwards.
Wonderful. And if you want to know more about the Light Conversations with Professor Jared Cole, you can head to the Victorian State Library website or the Centre for Excellence in Exciton Science website as well. Professor Jared Cole, thank you so much for your time. And we really look forward to seeing how your light research and how quantum physics is going to revolutionise our silicon solar photovoltaic cells for the better. Thank you so much.
No problems. Thank you.
All right, so what if I told you that temperatures around the globe were cooling? Would you think I'd gone all climate denial there?
Yeah, a little bit, yeah.
Well, I don't know. It depends on what you're measuring exactly, doesn't it?
Yeah, I'm measuring, this is the point. I'm actually measuring body temperature, not
Right.
surface climate temperature. Human body temperature, apparently, is declining.
Oh.
Yeah.
So basically people are getting cooler.
Yeah, people are getting cooler.
All buying leather jackets.
I can see that,
and
Stu, in your black T-shirt.
sunglasses.
Wow, talk about having to read the fine print.
Yeah.
Global temperature's cooling
That's
in the
right.
human body.
That's right.
What's
yes.
going on, Chris?
So I was actually planning to bring a thermometer into the studio so we could do like an in-studio experiment. Probably a very unhygienic in-studio experiment. But I went to the chemist and they said, no, sorry, all sold out due to coronavirus panic.
Oh, right, of course.
So that's a thing. Anyway, so we're just going to talk about it instead, I'm
Can
afraid.
we just get someone's mum to come and put their hand on our
We could
forehead
do that.
and see
We could
how
do that.
hot we are? Like,
But-
that's scientifically viable,
I
isn't
reckon
it?
you could even do that, Stu.
Well, I've got a child.
Exactly.
So I just go, oh, yes, you're sick, go to bed.
Yeah. Or you're not sick, go to school.
Depending on my mood.
Yeah.
Well, let's be even less scientific and just ask you, what is normal human body temperature?
38.7? 37.
What do you say, Stu?
It's 37 point something, I think.
Well, there was that movie, that Betty Blue, known as in English, there was a French movie called 37.2 Degrees in the Morning.
Right.
And that was like supposedly 37.2. But normally, a lot of people know the American one where they use Fahrenheit and they say 98.6 degrees Fahrenheit, which works out to pretty much 37 degrees Celsius. And this is what, most people, because that is like the classical temperature that we all know. And except for those who say it's 38.7 degrees.
You were sick last week, Claire, so maybe that's... Maybe you were 38.7 degrees.
But the 37 degree temperature, which is the 98.6 degrees Fahrenheit, that actually came from a German physician in 1851, Karl Reinhold August Wunderlich. Wunderlich translates as whimsical. He used records, supposedly millions of records, taken from 25,000 patients in Leipzig, of armpit measurements, known as the axillary temperatures. And he came out with the average of 98.6 degrees Fahrenheit, or about 37 degrees Celsius.
So that's an average.
Yeah, that was an average, yeah.
Yep.
But there's, like I said, there's a new study that's been published in the journal eLife, scientists from Stanford University, that says that this figure is out of date. Their paper is called Decreasing Human Body Temperature in the United States Since the Industrial Revolution. Because they looked over this over a long period of time. Yeah. So we've got Karl Reinhold August Winzigel in 1851. They actually looked at data from just after that to see how things had changed. And so they used 3 data sets. The biggest one was the Union, or the longest running one was the Union Army Veterans of the Civil War study, which went from 1860 to 1940. And that measured temperatures over that period. There's also the National Health and Nutrition Examination Survey, which went from 1971 to 1975. And then the Stanford Translational Research Integrated Database Environment from 2007 to 2017. And they looked at all the measurements from these, and they tried to track these across time, how things had changed. And what they found was that there was a decrease, pretty much a steady decrease of 0.03 degrees Celsius per decade. And this agrees with more recent studies of averages of temperature, which basically comes out the modern average is about 36.6 degrees Celsius.
Wow. So it's not just because of better measuring equipment or anything like that?
Well, that is the interesting question, is how real is this? And there is certainly a lot of skepticism about this result, because it does sound a bit kind of weird. And certainly things would have changed over that time period. But you're looking at, the biggest study, the longest study, which was that Civil War study, that went for, what was that, about 80 years. You could see the decline in that study itself. So that, presumably maybe the measurement techniques had changed in that time, but you could see that within that study itself. It was consistent in the more recent ones, the same decline, as I said, and it worked out to independent studies, which now currently measure a lower temperature than was reported in the mid-19th century.
Wow.
And some of the errors that you might have imagined, though, as well, also could have led to should not have necessarily led to a decrease. So, for instance, I mentioned, Dr. Winzigel.
Yeah.
He took armpit temperature measurements. There was a transition to using oral temperature measurements, which generally should be warmer than the armpit measurements.
Yeah.
So you should have seen an increase by that, rather than decline. If that was the explanation. So look, like I said, a bit of skepticism, but they speculated on what could be the cause of it. So temperature is a measurement of your metabolic rate. So you wonder if there's a change in the metabolic rate of people. Well, this is done in the United States. People in the United States are generally getting had up with this fatter. So that would actually lead to an increase in temperature, because a higher metabolic rate, you should actually see, a higher temperature. So that's not the explanation. But one hypothesis, which sounds quite plausible, is that it could be due to reduced levels of inflammation, due to reduced infections. So, over that time period, we've had antibiotics, we've had vaccines, we've had improvements in hygiene and water quality, all this kind of stuff. And certainly in the early studies, they found people with chronic tuberculosis infections and that sort of thing had a higher temperature. So that could be part of the explanation, but then you would sort of expect to see it level off as these improvements come on board. So they kind of talk about that a bit. They say that in the more recent times we've still had things like gum disease as being a form of inflammation. You've still got these days you have people taking a lot more anti-inflammatory drugs like aspirin and statins and those sort of things, which could be leading to decreases in the temperature. But really you need to compare it to say countries that don't have as good health systems, perhaps. They did mention there was a small study from an area in Pakistan that did show kind of higher average temperature, but this kind of hasn't really been verified as part of this study. Another possible explanation is that changes in the environmental temperature, not again due to climate change, but due to things like air conditioning. Mm-hmm. So, our base metabolic rate will go up or down. Will go up generally when we're trying to adjust our temperature. So, for instance, if we're in a too hot an environment, we need to try and adjust our temperature. If we're in a too cold environment, so the fact we have now like steady climate control indoors might mean that people are, don't have to expend as much energy to get to the right temperature. I don't know. This is a lot of speculation. They haven't really found a mechanism. It is really intriguing, though, that what we believed to be the human body temperature is not actually the truth. I did see what the official story is. Check, government health websites. The federal government's Health Direct website actually says normal temperature is around 36 to 37 degrees Celsius. So, they seem to be fairly accurate.
Or hedging their bets.
Yeah. Generally, fever, which is like your high temperature, that is considered a fever if it's over 38 degrees.
Right.
So there's a fair bit of margin there. If it's in that 36, 37 range, 38 degrees. So, sorry, Claire, your 38.7 was way out. But yeah, look, something really interesting to keep an eye on, and maybe go and measure your own temperature and see what you get, and let us know if you think that you are, let us know if you're sick.
Yeah, or maybe just go to a doctor.
Go to a doctor, perhaps, yeah.
Yeah. And that's all we have time for on our first edition of Lost in Science for 2020 with the whole team in the studio. Thank you so much for sticking with us, and a big thank you to Professor Jared Cole from RMIT University and the ARC Centre for Exciton Science. Lost in Science is recorded in the studios of 3CR in Melbourne and broadcast across Australia on the Community Broadcasting Network with the support of the Community Broadcasting Foundation. You can reach out and get in touch with us. We always love to receive your emails at lostinsight@gmail.com. If you want to email us, you can get in touch with us on Twitter. We're Lost in Science 1. We're also on Facebook, where we are Lost in Science on 3CR. Or you know where to find us on your radio or your podcasts this time next week, or wherever you download them, when Stu, Chris and Claire get Lost in Science.
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.